So we've been talking about determinants and how to find them and then using them and letting them tell us something about our major C's. But we haven't really talked about what a determinant might represent. So let's do that. So we're going to start off. I'm going to start on, ignore the eraser looking thing for just a second. We'll talk about that in a minute. So what I'm going to do is I'm going to start off with these two vectors here. And I'm going to plot these vectors. So I'm going to let v1 be this red vector. We'll let v2 be a blue vector. And I'm going to create the parallelogram that would be created if we were thinking about adding. So when thinking way back to that first week, in that vector video, he talked about the parallelogram that gets created by two vectors. So we're going to create a parallelogram, right? So my v1 vector is 1, 2. So this guy here. And my v2 vector is 3, 1. Oh, I just messed that up wholeheartedly, didn't I? 1, 2 would be that guy. 1, 2, let's put him here. There we go. There's my 1, 2 vector. Okay, and then 3, 1, that's this guy. Okay, and if we take and do the parallel vectors that create the parallelogram, hey look, we have a beautiful little parallelogram. And I don't know about you, but but there's ways to find the area of parallelogram. If you think back to geometry, what we're going to do is we're going to enclose our parallelogram in a rectangle and then subtract out the things that we don't need. So I'm going to make this rectangle here, right? And as you can see, so this is a rectangle of height 3 and width 4. So just go with me on this one. But if I want to remove these things, so what I'm going to do is I'm going to break this down into a couple of shapes. So I have a lovely bit of coconuts here, and by that I mean I have this little triangle right here that is a 1 by 2 triangle, and I have that exact same triangle over here that is also a 1 by 2 triangle. Then I have some beautiful little triangles over here. Nope, wrong color. Some beautiful little triangles over here. I have this guy, which is a 1 by 3 triangle, and his counterpart hanging out down here, also a 1 by 3 triangle. And then I have this leftover space here where I have these little squares. Turns out they're squares in this case, not always the case, but they are in this particular case. And I guess yellow is a terrible color here, so we'll make it purple. So let's get rid of some of these. There we go. Okay, let's make these little purple squares. We like purple squares. Okay, and for fun, so again, this is a 1 by 1 square, is a 1 by 1 square. So let's talk about the volume here, and by volume I mean area. So I'm gonna use some colors. So my outside is actually a combination. So this 4 is really a 1 plus a 3, right? If you look at it this way, so it's this 1 and this 3. And this 3 is really our 2 plus a 1, right? Now the colors are important, and the fact that I wrote those as a sum is also important. Here's what we're gonna do. So the outer volume area, the outside area is that 1 plus 3 times our 2 plus 1. Okay? And then we're going to subtract out of it all of those things that I highlighted. Now, the area of a triangle, right? The area of a triangle is equal to 1/2 base times height. Let's make that a base. But because I have 2 of these, that means that the red area that I've highlighted, if I squish those two red triangles together, it's now a rectangle. So I'm going to subtract out the 2 times 1 that represent those two triangles, right? So these are our two red triangles. So this is the area of the two red triangles. I need to subtract out the area of the two blue triangles. And again, 1/2 base times height, but I have two of them, so squish them together and just get a rectangle. So this is a 1 times 3. So that's the area of our two blue triangles. And then lastly, I'm going to subtract out, now this time I need 2 of these. So I need 2 of my 1 by 1 squares. So this is the area of our two purple squares. You ready for this? I'll blow your mind. Okay, probably not. I'm gonna multiply this thing out here. I'm gonna keep my colors because watch what's gonna happen. I'm gonna do 1 times 2, so I have 1 times 2, or 2 times 1, doesn't really matter. And then I have 1 times 1, so 1 times 1, right? That's these two. And then I have a 3 times 2, 3 times 2. And then last but not least, I have a 3 times 1. But then we're going to subtract these things out. So we're subtracting out a 2, right? We're still subtracting a 2 times 1, right? That's that guy. I'm going to subtract out a 1 times 3. And, oh, hey, I'm going to put that over here. 1 times 3. Okay. And then I also need to subtract out my 2 of my 1 times 1s. And watch what happens here. Stop it. Okay. Those guys will cancel. Those guys will cancel. One of these 1 times 1s will cancel. And what I'm left with is 3 times 2 minus 1 times 1. You ready for this magic? That looks a lot like a determinant, doesn't it? In fact, watch this. If I take this vector, no, okay, switch those. Doesn't really matter. There's not much to it, right? If I took this vector and I found its determinant is 1 times 1 minus 3 times 2, but because we're talking about area, so this gives me -5. This gave me a +5. So the area here was 5. The determinant was -5. So, oh, hey, look. If I take the absolute value of the determinant of A here, there's A. Ooh, and look, oh, A came from that guy. The determinant of A, if I take the absolute value, is 5, which is equal to the area that we found for this lovely parallelogram in a very, very complicated way. And I'm sorry, but that's just the way it goes. Now, so that's what happens when we, in 2 dimensions, if our vectors are elements of R2, right? So notice these are all elements of R2. Now this symbol, I'm not sure if we've talked about it. This means elements of, or means pieces of, or in, contains, all those kinds of things. But it's a mathematical symbol for elements of, and we use that for sets. So that's going to come back up in a later video or two, but just keep that in mind. So in R2, our vectors create a parallelogram, right? Parallelogram. And it turns out if we find the determinant of the matrix that is created by putting our vectors into that matrix, so the columns become the matrix, or the vectors become the columns of the matrix. If we find its determinant, take the absolute value of it, that is the area of the parallelogram. In 3 dimensions, what happens is if I have 3 vectors in 3 dimensions, I end up with something called a parallelepiped. Parallelepiped. And this parallelepiped, if you're trying to, like, there's a picture of this, but what this always reminds me of is those pink erasers, right? So if you ever have one of those pink erasers, that's kind of what a parallelepiped looks like. Now, it could be a little bit of a skewed parallelepiped, but that's kind of what it looks like. It's fun, right? So our theorem says that we can either find the volume or the area by finding the matrix that is represented where the columns are the vectors that were given, and we find the absolute value of its determinant. Yay. Okay, let's find an example. So we're going to find the area of this parallelogram determined by these points. And I'm going to plot them. So I have the point -2, -2. It's this guy here. 0, 3. That one. 4, -1. And 6, 4. 4. That guy. So here we go. Here's our parallelogram. Now we could certainly find the area of the square that, or the rectangle that encloses it, and do our subtraction thing again. Or we could use our vectors to make a matrix, but I don't have vectors, right? All of the vectors that we've talked about so far are vectors where they start at the origin, and none of my points starts at the origin. So these are not vectors, or at least not in the sense that we've been talking about them in linear algebra. Oh, goodness. These are not vectors as we know them. So what I need to do is I need to shift this whole thing in some direction so that one of my points, or one of my vertices of my parallelogram, is on the 0, 0 position. So it seems pretty easy to just shift this guy up there. So all I'm going to do, so for each of these points, I'm going to shift them over 2 and up 2. If you remember in geometry, this is a transformation, right? This is just a shifting transformation, either up or over. So I'm going to go up 2 over 2, up 2 over 2, up 2 over 2. And now I have a parallelogram where these guys, this one here is one of my vectors. So there's a vector. And this guy here is also a vector. So we need to figure out what those vectors actually are. So V1 here, my blue vector, is 1, 2, 3, 4, 5, 6. That's 6, right? Whatever this point is, plus 2, plus 2. So 6 in the x direction, up 1 in the y direction. And our V2 vector is 2 in the x direction and 1, 2, 3, 4, 5 in the y direction. So that makes my matrix 6, 1, 2, 5. And we're going to take the absolute value of the determinant of that. Okay. So these straight lines are not the same as the determinant straight lines that we've used in the past video. These mean absolute value, right? This means absolute value. So the determinant of A is 6 times 5 minus 2 times 1. 6 times 5 is 30, minus 2 is 28. So the area of this parallelogram is 28. The area of the parallelogram is 28. Why not? We'll make an actual statement. Who doesn't love a statement? Okay. Let's take this idea and talk about it in terms of transformation. Who doesn't love a transformation? So our linear transformations, different than the transformation I was just talking about squishing that thing up into the right position. If I have a 2 by 2 matrix and my transformation takes, so we're talking about a transformation, right? So where we have AX equals B, something like that, or just AX, there we go. Transformation is equal to, transformation of X is AX. There we go. The area of this transformed parallelogram is equal to the determinant of A times the area of S. Well, this is just the original parallelogram. And it is just the determinant, so it's the absolute value of the determinant of the matrix with columns equal to the vectors. There we go. Same thing here. It says area of S, same thing, except for parallelepiped instead of parallelogram. So here's what's going to happen. All right, we're going to do an example of this. So here's my A vector, and we need to find a couple of things. So we're going to start off, and we're going to kind of compare a couple of things that are happening here. And we're going to color things because colors are great. I'm going to let V1 be blue, V2 be red. These are the same vectors as before, except for I probably just switched their colors because why would I do that? Why would I be consistent? And 3, 1. Yep, I definitely switched their colors. Right. So here's the original S. So this is S, right? That's our original parallelogram. And we need to define a couple of things. So first, we need to know what T of V1 looks like. Well, all that means is substitute V1 in for X, so that's A times V1, which is -1, -3, 2, 4, times 1, 2. It's going to give us -1 plus 4 gives us 3, and -3 plus 8 is going to give us 5, right? And let's see, double check that we're looking at the right numbers. Hey, look at that. She can do algebra. By algebra, I mean the other thing. All right, so same thing for V2, right? I'm going to take that vector matrix times the vector 3, 1, and I'm going to get -1, -5, I believe. Yes. So I have those, and we already figured out, right, in the last lovely video. So from the last example, we know that the area of S is equal to 5. Right, so we already figured that out by finding the determinant of that matrix. If we didn't know that, what we could do is we could find the determinant, but the area of S here is the determinant of the matrix 1, 2, 3, 1, right, or the absolute value of this. So if we didn't know, but we do. So I'm going to actually plot this new, what this new parallelogram looks like, just to show you that we actually get another area here. So 3, 5. We'll let this guy be green. 1, 2, 3, 2, 3, 4, 5. There's my green guy. And then we'll let this guy be our purple. And I think we're going to go off the page. 1, -5, 1, 2, 3, 4. It's down here somewhere. Not a lot of great planning going on there. So it's going to be there and there. So this is T of S. That's our transformed parallelogram using our matrix. And the area of that is the determinant of our new matrix, 3, 5, -1, -5. And we get 3 times 5, so 3 times -5, and absolute value. Don't forget that absolute value because we're talking area. Minus 5 times -1 is going to give me, so I get a -15 plus 5 gives me negative 10, but we're going to do absolute value. So the area of T of S is 10. Now, you ready? I don't even actually need to do this multiplication, so I don't even care what happens here. I don't actually need to do that because I can find the determinant of A, right, by taking, and that's the original matrix, so determinant of A is negative 1 times 4 minus 2 times negative 3 is going to give me 2. And again, we'll absolute value that along the way. At some point it was probably negative, who knows. So that's 2. And if I just take the two matrices, and if we just take the determinant of the original, the matrix created by the original vectors, right, we found this determinant, the absolute value of that was 5. If I take 2 times 5, I get 10, which is exactly what I got here by having to find those vectors. So again, don't need to find those vectors. I can just take the determinant of the A that's given, determinant of the vectors that are given, bada boom, bada bing, we're done. So, what are we talking about next? Ooh, well, that's it. Look at that. Beautiful.